Everybody, this is Urwa, a high school computer science teacher, and this is what I'm working on today. This is a CBC V2 Robotic Controller. It's a simple controller, robotic controller intended to be used by teenagers as part of the butt-ball robotic competitions. And what I'm showing here is the PWM modulated drive waveform of a motor. Like many other robotic controllers, it has many inputs, some analog, some digital, and it has some drive ports. On this one in particular, one has 4 motor drive ports, like continuous rotation motors, and 4 servo ports intended for driving a stepper motor, a motor that points in a specific direction, that rotates continuously. So I'm using the normal motor drive ports, which are PWM modulated. What does that mean? Is that, as you can see, the signal used to drive the motor is made up of cycles, and those cycles are fixed width, but the duration of time during which the pulse is on is variable, and that we call pulse width modulation. You change the width of the pulse to deliver a varying amount of power to your motor. Now, very cool. In order to get a clean display of this waveform, I had to use a fixed duty cycle or a 50% duty cycle motor signal in order to synchronize the oscilloscope, which is what we call the trigger. So the trigger signal is external, as you can see, which I get from the port in here, which has a fixed duty cycle. But the one that I end up displaying is the one that is sawtooth, like it's a sawtooth waveform, or basically like I keep on varying the duty cycle up and down all the way up to 100, then I go all the way down to 0. So that's how it works. I've used another piece of instrumentation that I have here, which is the function generator. Our function generator has a frequency counting function. What does that mean? By connecting a periodic signal to this device, it can tell you how many times it repeats itself per second, the frequency. So this one reads at 93 kilohertz. So seemingly we have pulses at 93 kilohertz, and the width of the pulses is being modulated to vary the amount of power. Now, why am I doing this? The reason why I'm doing this is that I want to understand what kind of output I can provide to the external world via those motor drive ports, and I want to see if I can use that to drive any arbitrary device that I want. Basically, I'm really interested in using this to drive a pair of speakers, because the speakers on the inside do suck big time for some reason. I don't know why. There seems to be something wrong with the drive circuitry of the speakers. The sound is really bad. And what I discovered as well is that there's a function in the C library, in the KISS IDE, called tone, which allows you to emit a tone of a specific frequency, but for some reason it's not implemented. So when you try to use it, it shows the message must function not implemented on the LCD. So I'm trying to connect some external speakers, and to do this I need to understand the kind of waveforms that get generated on the motor ports when you use the motor function. So also one of the other reasons that made me do this is that, like, I assume that when you drive a pair of speakers using a PWM ratio of 100%, you should get no sound at all, because you'll end up with a continuous function. Now, let me demonstrate this. Like, I programmed this, that once I press the A or the B button, any one of them, what will happen is they will get locked at the 100% modulation ratio, which just happened right now, which is what happened. Now, here, as you can see, ideally you should have a continuous DC signal, which should not emit any sound on a pair of speakers once connected. So let's try to turn on the speakers and see what kind of sound gets generated. As you can see, it's very, very loud, which is caused by those ripples or by those spikes. To take a closer look into those spikes, what I'm going to do, I'm going to change the coupling into AC, which will remove the DC component, and I'm going to decrease the amount of volts per division, to take a closer look into the ripple. And as you can see, there's quite some ripple in there. Now, if I adjusted it to 0.2 volt per division, as you can see, we have 0.4 worth of positive ripple or positive spike and almost -1 volt. 1, 2, 3, 4, 5. You have 5 divisions are spanned in the negative direction, which correspond to -1 volt. So that's a lot of spikes. So those spikes, those harmonics, are what causes the loud sound. So let's try again. Yeah, so as you can see, I'm hoping that by connecting some sort of filter circuit to the motor drive output that I can smooth the signal, and considering the fact that the frequency of the pulse drive is high, like compared to audio signals, the highest usable signal in audio is 20 kilohertz, makes me think that this might be possible. So I will try to do this next. Thank you very much. I wish that you found something interesting here, and that this will help you try to push your CBC version 2 controller to its limits. See what you can do with it. Thank you very much.